In this video, we're going to cover section 7.5 on more trigonometric equations. So in the last section, we covered some basic trigonometric equations, i.e. equations with trig functions in them, and we solved for the angles. Here we're going to do the same thing, except for the equations are going to be just a little bit more complicated. So our first example is going to be sine squared of theta is equal to 5 minus 2 cosine squared of theta. One thing we might try, and this isn't entirely obvious, but after you do several examples, you might try this. So if we add 2 cosine squared of theta to both sides, so let's go ahead and do that. And what do we get? Well, we get sine squared of theta plus 2 cosine squared of theta is equal to 5. Sorry, I was off the page, or off the video. So if we continue with this idea, all right, we move this over. Well, we know that sine squared plus cosine squared is 1, using that Pythagorean identity. So we can factor out one of our cosine squareds here, or really just separate this addition, right? So sine squared of theta plus 2 cosine squared, so that is just a cosine squared of theta plus another cosine squared of theta is equal to 5. Sine squared plus cosine squared is 1, so this becomes 1 plus cosine squared of theta is equal to 5, or in other words, cosine squared of theta is equal to 4. Except, what do we know about cosine squared? Cosine squared has to be between 0 and 1. So there are no solutions to this problem. All right, so that one ended up being not so bad once we saw what to do at first. It's not always obvious what to do, as I was saying, so really you just want to build up your intuition on these problems and recognize patterns and use your formulas. Think to look for those formulas, right? I know the Pythagorean identity. One of the Pythagorean identities is cosine squared plus sine squared is 1. So I knew to look for that as a possibility once I saw some sine squareds and cosine squareds in the same equation. And that's what I did, is I moved over the 2 cosine squared over to the left so that in fact we do get to separate one of those cosine squareds out and have a expression here that we can change to something simpler. I want to continue on with another example here. Tangent of theta plus 1 is equal to secant of theta. This one is not obvious at all either at the beginning, but I'm going to go ahead and tell you that we can try squaring both sides. If we do that, we get tangent of theta plus 1 squared is equal to secant squared of theta. Right? We've just squared both sides of the equation here. So let's go ahead and multiply out tangent of theta plus 1 times tangent of theta plus 1. All right, I'll write that real quick. If we're squaring something, that means write it down twice and multiply. So tangent of theta times tangent of theta is tangent squared of theta. Then 1 times tangent of theta plus another 1 times tangent of theta is 2 tangent of theta. 1 times 1 is, so plus another 1. And this is equal to secant squared of theta. Well, tangent squared plus 1 here, so this and this is another Pythagorean identity. And the Pythagorean identity is tangent squared plus 1 is equal to secant squared. So this is in fact secant squared of theta plus 2 tangent of theta is equal to secant squared of theta. So in fact we get just 2 tangent of theta is equal to 0, or in other words, tangent of theta is equal to 0. I circled that. We don't need to do that yet because we're not quite done. We want to find the theta that makes this true. Well, there are two thetas that make tangent of theta equal to 0. All right, tangent is sine over cosine, so when sine is 0, is at theta equals 0 and theta equals pi. Except we have a bit of a problem here. And that is that we squared both sides, so we might have gotten some extraneous solutions. Okay, so originally it looks like theta equal to pi k should be our solution, except we squared both sides, so we check for extraneous solutions. And what do I mean by that? I mean, again, some of these solutions actually may be false that we got. So let's check. First thing we want to try is theta equal to 0. Well, tangent of 0 plus 1 is equal to secant of 0. Tangent of 0 is 0. Secant of 0 is 1 over cosine of 0. And cosine of 0 is 1, so that's 1 over 1. So we in fact get 1 is equal to 1. Yes. So theta equals 0 is a solution, and thus theta is equal to 0 plus 2 pi k will always be a solution. The other one we want to check is theta is equal to pi. All right, so let's see. Tangent of pi plus 1 is equal to secant of pi. Tangent of pi is 0 plus 1 is equal to secant of pi is 1 over cosine of pi, but cosine of pi is negative 1, so this is negative 1. And we know, in fact, that 1 is not equal to negative 1. So theta is equal to pi is an extraneous solution. We got a wrong answer in there. And why does this make sense? Right? If we plug in pi up here into this original equation, we get 1 is equal to negative 1 as we just showed. But ultimately, the first thing we did was we squared both sides. So if theta was pi and we squared both sides, we would get 1 is equal to negative 1 squared, which is also positive 1. So we get 1 is equal to 1, which is true. And that's why that extra solution showed up here. And so by plugging in here at the end, by plugging both of our answers in, we found out that 1 was extra, like it was wrong. So in fact, the correct solution is theta is equal to 2 pi k. And that is it for part B here. We actually have 2 more examples that we want to go over. So I will do that here. So part C says 2 sine of theta over 3 plus the square root of 3 is equal to 0. I want to go ahead and solve this. So let's move the square root of 3 over to the other side, and we get 2 sine of theta over 3 is equal to negative square root of 3. This implies that sine of theta over 3 is equal to negative square root of 3 over 2. Well, when is sine of x equal to negative root 3 over 2? Let's think about the unit circle. We can have x equal to, let's see, this is pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and then 5 pi over 3. So those two solutions give us sine of x is negative root 3 over 2. But that's a problem here. Because we don't want what x is, we want what theta over 3 is. Or we want what theta is, but we know what theta over 3 is, right? So theta over 3 is equal to, one of our solutions is 4 pi over 3 plus 2 pi k. And if we multiply by 3 on both sides of this equation, we get theta is equal to 4 pi plus 6 pi k. We also said that theta over 3 could have been 5 pi over 3 plus 2 pi k. So in fact, if we multiply by 3 again on both sides, we get theta is equal to 5 pi plus 6 pi k. So we got two solutions here for theta to solve our equation. Oops. All right. So we're going to do the last problem here for section 7.5, and that is to solve by factoring. And this ugly looking thing here that says secant of theta, tangent of theta, minus cosine of theta, cotangent of theta is equal to sine of theta. So to solve this by factoring, first thing we want to do is we want to convert to sines and cosines. So let's do that. So we get 1 over cosine of theta times, right? So secant of theta is 1 over cosine theta. Tangent of theta is sine of theta over cosine of theta. And then we get minus cosine of theta times cotangent of theta is cosine of theta over sine of theta. And this is equal to sine of theta. Okay, now we have some stuff on the denominator here. So the first thing I want to do is I want to multiply by cosine squared. If I multiply by cosine squared on this term, so let's multiply by, well, I don't want to write that. Multiply by cosine squared of theta. So if we do that on this first term, we get sine of theta. If we do that on the second term here, we get cosine squared times cosine squared. So that's cosine to the 4th of theta all over sine of theta is equal to cosine squared of theta times sine of theta over on the right. Then we want to multiply by sine of theta to get that off of the denominator. So on the left here, we get sine squared of theta minus, here the sine of theta will just cancel, so it's minus cosine to the 4th of theta is equal to cosine squared of theta, sine squared of theta, because we multiplied by another sine here, so this became sine squared. Okay. Then we were told that we want to factor in this problem. We were told that at the very beginning of the problem. So let's see if we can find a way to factor now. Notice that we have a sine squared in both of these terms. So how about I move this sine squared over to the other side and the cosine 4th over to the right. So we get sine squared of theta minus the term that was on the right, cosine squared of theta, sine squared of theta. And this cosine to the 4th, we move over to the right, so we add it on both sides. So it's now cosine to the 4th of theta. All right, so again, that's cosine to the 4th of theta over on the right. We can factor a sine squared out, so sine squared of theta times, if we factor out a sine squared, we get 1 minus cosine squared of theta. And this is equal to cosine to the 4th of theta. 1 minus cosine squared, we can use our Pythagorean identity. This is just sine squared. So this is sine squared times sine squared of theta is equal to cosine to the 4th of theta. That means sine to the 4th of theta is equal to cosine to the 4th of theta. If we take the 4th root of both sides, this tells us that the absolute value of sine of theta must equal the absolute value of cosine of theta. So when do those equal each other? Well, those equal each other at these angles. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And notice cosine and sine don't equal each other along this line, but their absolute values do equal each other. And recall that that's really the solution to our equation that we got. So what are those thetas? Well, those thetas are pi over 4 plus pi k and 3 pi over 4 plus pi k. And that is it for all of the examples from section 7.5 that we wanted to do. And that actually ends chapter 7.